I would like to thank the organizers of this session for the possibility of presenting our results at the conference. We are working with the problem of the structure and dynamics of the nanophases in different porous materials like multi-wall carbon nanotubes, hierarchical carbon, activated carbon fiber, CMK3 ordered carbon, SBA15. This problem has a fundamental in many fields like microelectronics, gas sensing, environmental protection, energy storage, gas separation, solar cell, and also in medicine, especially in the drug delivery problem. Our aim was to understand the phase behavior of simple fluids within nanopores like activated carbon fiber, which form the slit pores, multi-wall carbon nanotubes, which form the cylindrical pores, carbon mesostructure, which form cylindrical form. They are the carbon reverse replica of the ordered SBA15 porous materials. We are working with the problem of the phase transition, melting phase transition of the substances in porous matrices. We find that the temperature of the melting of the substances in porous matrices is quite different than for the bulk system. We find that we can observe increase of the melting temperature in pores relatively to the bulk. We can observe decrease of the melting temperature relatively to the bulk. And this increasing is a function of the pore size. So on the basis of the literature, it was considered now that freezing at the temperature of freezing in pores can be expressed by two variables, pore width and also alpha parameter. Alpha parameter, it is the ratio of the energy of the fluid wall to fluid. And the next interesting things that is frequently observed that phase transitions which only occur at high pressure or at low temperature in the bulk phase take place in the confinement place and the ambient condition. Examples of such a phenomena include rate of the chemical reaction. It was shown that rate of the chemical reaction in pores is typical like rate of the chemical reaction under the high pressure, and solid phase observed in pore are typical like high pressure solid phases, and also spectral properties of the confinement system is just similar like the high pressure effect. So now the expectations are that the carbon nanopore space can play a role of high pressure reaction cell. The origin of this quasi-high pressure effect of the confinement has been attributed to the strong intermolecular forces between the walls of the pores and the molecules of the confinement phase. It was shown that the pressure in pores, tangential pressure and also pressure normal to the wall, can be strongly affected by the choice of adsorbate and the porous material, and is also can be described like a function of the pressure versus the wettability alpha parameter. The tangential pressure has a very high alpha, have very high value as a function of the alpha parameter, and pressure normal to the pore walls is also changed but not so high. We describe the high pressure effect in nanopores for water confinement in activated carbon fiber. The activated carbon fiber consists of the small graphite particles of 2.5 nanometer size, and the pore system forms a slit-shaped pore of approximately 1.4 and 1 nanometer size. On the basis of our wax results, we find that the structure of the ACF nanocrystalline has a turbostratic character, and the lattice constance is 3.78 angstrom. When water was absorbed by ACF, we find that the structure of ACF is changed, and the lattice constance is the same like the lattice constance in graphite, and the structure of the turbostratic ACF structure is typical for the graphite. The magnitude of the observed shrinkage in interplanar distance in ACF we can calculate using the elastic modulus formula, where the tensile stress it's just the pressure normal to the pore. We find that the tensile strain from experiment for ACF with the pore size 1.14 is 0.48 angstrom, and for different pore size of ACF we find quite different results, so we find the negative change of the interplanar distances. Using the transverse compressive modulus, typical for the pitch-based mesoporous ACF, we were able to calculate the pressure normal to the pores. For the ACF with the pore size 1.14, we find that the pressure normal to the pores can be about more than 400 megapascal. For smaller pore size of ACF, we find that it is a negative effect about 100 megapascal. Similar results, similar measurements were done for CCl4 placed in ACF, where we find the normal pressure range of the 300 megapascal. These results are quite good, has a quite good agreement with the simulation results. So it was found that pressure normal to the pore as a function of the pore size for ACF is the oscillating function, and our experimental points lie quite good at this curve. The similar results for CCl4 in ACF with the pore size 1.14 nanometers. We study the structure of ice in confined in different porous matrices. I would like to remind that phase diagram of bulk water is very rich, so dependence of the pressure and temperature, we can distinguish 16 polyform form of ice, which are different in the structure and properties. In the ambient pressure, the ice has a hexagonal structure, so we have a hexagonal ice which is formed at natural snow and ice on Earth. At the lower temperature, with the higher pressure, we can distinguish the different form of the ice, which is called cubic ice, with a different space group. Cubic ice is the metastable form of ice that can be formed by condensation of water vapor at ambient pressure or by reducing the pressure on high pressure ice at 77. As we can see that cubic ice is much more packed than hexagonal ice. We perform X-ray diffraction experiment for water inside different porous matrices like SbA15, K86 silica spheres. They are silica matrices with a different pore size, and also carbon matrices like CMK3, CMK8, hierarchical carbon with the different pore size. We find that the structure of ice in each porous matrices is quite different. There are diffraction pattern for ice in pores of CMK3 with a pore size 5.6 nanometers. At the first, we perform DSC measurement to find the melting temperature in pore. So his flow release due to the melting temperature is shown like a peak in which we can find the temperature of the melting for the system. And on the diffraction pattern, we can see that at the temperature lower than the melting point, we can see the black peaks typical for the crystal structure. Analysis of the spectrum using the Panalytical High Score Plus program show that the spectrum obtained for this system is the typical for the theoretical spectrum showing by Malkin for the stacking disordered ice. So which means that we find that that ice observed in the system is consists of the partially of cubic ice and partially of the hexagonal ice. The similar results we find for ice confinement inside the pores of KIT with a different pore size. Again, DSC scan shows the melting temperature of substances inside the pore, and we can see the black peak at the temperature lower than the melting point. And we find that the ice observed using this method is consists of the cubic and hexagonal ice, but with the different percentage. Because our diffraction pattern was very similar for the stacking disordered ice showing by Malkin, we interested of the stacking disordered ice, which is consists of the hexagonal and cubic layers. Its growth due to the heterogeneous nucleation and the bulk system is observed in the process recrystallization from high pressure phases, heating of glassy aqueous solution, freezing of nanometer scale water clusters. Stacking disordered ice does not possess cubic or hexagonal symmetry, but it was recognized and identified to have a space group P3M. The marking theory predicts that during freezing of water, a two-dimensional nucleation process occurs, which results in the alternate growth in various combinations of hexagonal and cubic structure layer within ice crystals. Thus, the resulting ice is made up of combination of intertwined cubic and hexagonal stacking sequences. Our diffraction neutron measurement just confirm the results obtained from X-ray diffraction. We find that for ice observed in ACF and KAT6, we have a two structure of ice with a different content of the cubic and hexagonal ice. So we find that the hydrophilic surface on pores has a showing as a function of the pore size, showing the larger content of cubic ice than hydrophobic surface of the pores. We try to characterize the structure of the pores wall for silica SBA and carbon material. We use silica SBA like a precursor for synthesis of the ordered carbon material, and TM results show that it is very ordered system. And for carbon, on the basis of the EDS measurement, we can see very small amount of oxygen, which means that we have no practically functional oxygen group at the surfaces. We did also potentiometric titration measurement showing for these both different porous matrices, and it shows that for SBA15 we can observe the zero charge point at for pH. We can observe the value 4.5, and for carbon material it is a very higher value, 10.4. So the values of pH of zero charge point evidence about the difference of an activity of the silica and carbon surfaces. We also perform the contact angle measurements inside the pores. We wanted to find the influence of the micro roughness on wettability of nanoporous matrices. We use the capillary rise method to obtain the contact angle inside the silica pores, and also modified Washburn equation to calculate contact angle inside the pores. So we can see that contact angle inside the pores, it is so the contact angle versus alpha parameters has a very large value relatively to the smooth surfaces, which is shown on the blue line. So we can understand that melting process is described by Kaji-Baxter model, where contact angle inside the pores is higher than the contact angle at the flat surfaces, because not all drop of liquid has a contact with the solid surface. We can, on the basis of the Kaji-Baxter model, we can now the fraction of liquids which have a contact with solid matrices, and we find that this fraction is higher for OMC than for SBA15. We also calculate the work of immersed wettability, defined as surface tension cosine theta in pores, and we find that it is much larger for D2O placed in SBA15 than for OMC. So this result suggests that silica surface prefers creation of cubic ice fraction in disordered ice. As we can see, the content of cubic is larger in SBA than OMC. At the end, I would like to show our conclusion. The structure of ice found in carbon and silica mesopores is typical for the stacking disordered ice, containing the different ratio of the cubic ice and hexagonal ice, the hydrophilic surface of pore characterizing the stock value of wetting energy create in disordered ice much more rich on cubic than hydrophobic surfaces. The content of the cubic ice increase as pore size decrease for both hydrophilic and hydrophobic surfaces. And the last, maybe quite important information from this measurement, that the melting temperature of water in pores depends on the structure of stacking disordered ice, which is differ on the content of cubic ice. I would like to thank the person who was working in the subject, Professor Gabbins from North Carolina State University and his co-workers, and also my co-workers from Poznań, where the experiments were done. Thank you very much for the attention.